So dividing is our next topic. Just like with the product rule, we also have this rule with division. As long as your nth root of a and nth root of b are real numbers and b is not 0, it is true that nth root of a divided by the nth root of b is the same thing as the nth root of a over b. So when you're working with these divisions, or really fractions, our division rule is telling us that, if we have two radicals with the same index, we can rewrite that as a single fraction, or if we have a single fraction, we can split that into 2. So again, this putting it together, splitting it apart, we're going to be using them both, whichever one best suits our purposes, and doing our simplification. And so it is called division of radical expressions, but it's really more of a simplification of a fraction than it is actually a division. When you're asked to do these divisions, you are going to have to basically do manipulations until all 3 of these conditions are met. One of the biggest concerns that students have is they say, I just don't know when to stop. They just want to keep going and they don't know when they're done. And so to know when you're done, you have to learn these 3 things. All 3 of these conditions, you need to know them, and all 3 conditions have to be met for your final answer. Okay, so when you're working with a division of radical expressions, you have to just keep doing manipulations until every radical is simplified, the fraction is simplified, and no radicals remain in the denominator. So those are the 3 conditions that need to be met, and that's kind of what you're going for. So looking at this first division, we've got the square root of 49 over the square root of 100. And with each of these, you're going to have to kind of think about it a little bit before you start. Sometimes it's beneficial to, if you've got 2, separate square roots, it's going to be helpful in some cases to rewrite that as a single. In this case, it is true that this is equivalent to the square root of 49 over 100. Rewriting it as the square root of 49 over 100 does nothing to help me out. The only time it's helpful to have it as a single fraction is if, when doing so, you end up with a fraction that will reduce. 49 over 100 does not reduce, so rewriting this as this was not helpful at all. Okay, sometimes it is, sometimes it's not. You do want to think about it before you proceed. So I know that my 3 conditions that I want all my roots, my radicals simplified. I want, if the fraction simplifies, I want it simplified, and I want no roots in the bottom. And that's kind of the route I take. Often I'll look at the radicals first. Can I simplify the square root of 49? Yes, I can. 49 is a perfect square. The square root of 49 is 7. 100 is also a perfect square. The square root of 100 is 10. Okay, so I've done something. Let's see if my conditions are met. So I've simplified my radicals. Looking at the fraction 7/10, 7 and 10 do not have a common factor. So 7/10 does not reduce. And then the final of the 3 conditions is, did I put them on there? I did not, is that there's no root in the bottom. So, and that is the case. They do not have a root in the bottom. So, this is the simplification of the square root of 49 over the square root of 100. Next one, divide, assume all variables represent positive real numbers, again, so that we can use that division rule. So here I have a single fraction, and it's only beneficial to have this single fraction if what I have inside is a fraction that will reduce. B to the 7th over a to the 10th c to the 2nd, I cannot reduce that fraction. I don't have any, I've got b's in the top but no b's in the bottom, right? So I can't do any reduction. Same thing goes for my a's and my c's. So there's no benefit to having this as a single fraction. So I'm going to rewrite this as the division of 2. So the square root of b to the 7th over the square root of a to the 10th c squared. Okay, so I know that the three conditions that need to be met involve, one of the biggest is I want to make sure that all my radicals are simplified. If the powers are greater than or equal to the index, we know that we can do a simplification. So all of these can be simplified. B to the 7th is not a perfect square, so to do the simplification I need to break it up. And the largest perfect square factor of this is b to the 6th. So I'll break this into b to the 6th times b. So that numerator is the square root of b to the 6th is b to the 3rd. So we have b to the 3rd times the square root of b. Looking at the denominator, 10 and 2 are both divisible by the index 2, so I know that I can simply evaluate. These are both perfect squares. The square root of a to the 10th is a to the 5th, and the square root of c squared is c. So this is a to the 5th c. Going back to my three conditions, and unfortunately I don't have that on there, but here, can you see my, the three conditions in your notes are all radicals have to be simplified, the fraction itself has to be simplified, and no roots in the bottom, okay? And remember, that's if you don't know when to stop, you stop when all three of these conditions have been met, okay? So, have we simplified the radicals? Yes, we have. Can the fraction itself be simplified? So in terms of simplification, it would only be if, looking at the coefficients here, all the non-radical parts, there's nothing that can nothing we can cancel. So that fraction is simplified and we have no radicals in the bottom. So we now have all three conditions met, so our division is complete. Square root of 135 over the square root of 20. So again, you're asking yourself, does it serve any purpose to have this together? Can I reduce that fraction? And the fact that both both numbers end in either a 5 or a 0, so we know that they're divisible by 5. And don't forget that, if you're not comfortable with doing a reduction of fractions, you can do that on your calculator. On this calculator, this is my fraction button. So if I hit my fraction button and I type in 135 over 20 and hit enter, you see I get 20, can you see it? 27 over 4, which is the reduced fraction. So it is going to serve a purpose, generally speaking. Sometimes no. If this number is a perfect square, I would not have simplified. I would have left it as is. But since it's not, I will do that reduction. So that's the square root of 27/4. And now that my fraction is reduced, now it no longer serves a purpose as being one fraction, one radical expression. Now, to finish my simplification, I want to break it into the 2. So that's equivalent to the square root of 27 over the square root of 4. I know that I need all my radicals simplified. The bottom is easy. The square root of 4 is 2. I can evaluate that. 27 is not a perfect square, but it is divisible by 9, which is a perfect square. So I'll break it into the square root of 9 times the square root of 3. The square root of 9 is 3. So this is 3 root 3 over 2. Okay, can I stop? Have I met my conditions? So go back to that page. Let's look at the conditions. So, have I simplified all radicals? Yes, that 3 is not divisible by a perfect square, so I know that's done. Second condition is the fraction simplified, 3 over 2. 3 and 2 do not have common factors, so that's good. And final is no roots left in the bottom, and no root is in the bottom. So I have met all 3 conditions, so I can stop. Okay, that is the division. That is the quotient of that results from doing that simplification. Okay, the square root of 8/3. So first thing, looking at this, you know, does it serve a purpose to have it as 1? And sometimes, you know, I don't know if I haven't had any examples like this, but sometimes you're given maybe the square root of something over the square root of something, and if you notice that you could reduce if you put it together as a single fraction. So sometimes, you know, you'll want to, even if you were given 2 that were separated out, you might want to go ahead and put it together as a single fraction so that you can reduce before you do your simplification. But back to this. So 8/3 doesn't reduce, so I'm going to go ahead and split it into 2. So we've got the square root of 8 over the square root of 3. I know that I want my radical simplified. 8's not a perfect square, but it is divisible by 1, 4. And so the square root of 8 is 2 root 2. The square root of 3 does not simplify. So with everything that we've discussed, you know, we've done our simplification of radicals. The fraction itself does not simplify, you know, 2 and 1, no. And then also if your radicants had common factors, you could reduce 2, but they don't. But I can't stop because I haven't met that third condition. So with what I have here, those first 2 conditions are met. My radicals are simplified and the fraction is simplified. But the third condition is no radicals in the bottom, right? And so I have a dilemma. I mean, I know I can't stop, but I don't know what to do from here. And so what you need to do from here is what we will discuss next. So this is to be continued here. Okay. We need to talk about what we need to do first before we can finish this out. So, rational denominators. Typically speaking, when we write in math, when we write an expression, we typically want to do so with rational denominators. Going back, square root of 3 is an irrational number. Okay, if you look at on your calculator and the square root of 3, mine's just going to spit this out. Let me get a decimal. You know, if you look at the decimal equivalent, and my calculator is limited in what it can display, but if it could actually display the value of the square root of 3, what we would have is a decimal number with a decimal part that never ends and never repeats. Okay? These radical numbers, these square roots of 3s, square roots of 5s, you know, if you cannot get it to simplify, those are actually irrational numbers. Okay? So the square root of 3 is an irrational number. And what we're saying is typically we want rational numbers, numbers that can be written as ratios in our denominator. And so, if you write a fraction with a root in the denominator, then the denominator represents an irrational number. And so to make the denominator rational, we are going to be rationalizing. So that's where this word comes from. Rationalizing the denominator is doing what we can to make that denominator rational. Or in this case, no more square roots in the bottom. Okay, so going back to the example that we had. We've already done this, and actually we've gone one step further, and we've written this as 2 root 2 over the square root of 3. Okay, I know that this is not cool because I've got the root in the bottom, and I know that that root, that's an irrational number, and I want a rational number, so I need to rationalize. Okay, when you are rationalizing, you have to write an equivalent fraction. Okay, we're trying to, it can't change its value. So it has to be an equivalent fraction that does have a rational denominator. And you know, go back to what you know about fractions. Think about if I ask you to add 1/2 plus 3/4. Okay? You know that to be able to add 1/2 and 3/4, you have to have a common denominator. And that would be 4. And so we want to take this 1/2 and create an equivalent fraction that has a 4 in the bottom, right? And so when we do that, to make an equivalent fraction, you always, if you're multiplying the denominator by 2 to get it in fourths, you have to multiply the numerator by 2 as well. So anytime, think about that, okay? So we are making an equivalent fraction, and to create an equivalent fraction, whatever you multiply the denominator by, you have to multiply the numerator by as well in order for that to be equivalent, okay? Also, so that's one thing to keep in mind is you're making an equivalent fraction. The second thing to keep in mind is that you are specifically trying to rationalize, okay? So what you choose to multiply by should make the radicand of the denominator a perfect square so that you can evaluate so that you have no square root in the denominator. Okay, so I am going to rationalize. Let me change my color here. So I'm going to write an equivalent fraction. I'm going to multiply the numerator and the denominator by the same thing. And what I choose is going to be a number so that the product of these needs to be a perfect square. Okay? So you can do anything that you want, but you know that if you take a number and multiply it by itself, that you will get a perfect square, right? 3 times 3 is 9, and that is actually the easiest route to go. I mean, there are infinitely many numbers that you can put here. If you multiply 3 by 12, you get 36, which is also a perfect square. So we could do a 12 and a 12, but trying to find the easiest route to take would be multiplying 3 by itself. So what we end up with when we do after we multiply to write our equivalent fraction, we've got 2 and then multiplying the radicals together, the radicands, 2 times 3 is 6. So this will be 2 root 6 all over the square root of 9. So again, always keeping in mind, it has to be that all of my radicals are simplified, the fraction is simplified, and no root in the bottom. The square root of 9 is 3. 6 is not divisible by a perfect square, so I can't simplify that at all. And 2/3 does not reduce. Some people try to reduce the 6 with the 3 here, but it's not that 6 is a factor, or that 3 is a factor of the numerator, but rather root 3. So you cannot cancel a radicand with a radical number with a non-radical number. So it would only be with the coefficients or if radicals, radicand with radicand. Okay, so this is a fraction that meets all 3 of our conditions, and so now we can stop. Again, the goal of rationalizing is to make the denominator a rational number, okay, or no root in that denominator. Do one more here. So we've got 2 root 3 times the square, 2 root 3 over the square root of 32. So if 3 and 32 had a common factor, I would go ahead and reduce, which is really what you do when you put it together as a single fraction and reduce that fraction. But 3 and 32 do not have any common factor, so there's nothing I can do with that reduction. 32 is divisible by a couple perfect squares. It's divisible by both 4 and 16. 16 is the largest, so that's going to be the route I take. So the square root of 16 times the square root of 2, this would simplify to 4 root 2. So what we have is 2 root 3 over 4 root 2. And there's lots of routes that you can take. You might recognize now that 2/4 can reduce. We can go ahead and do that if we want. Whoops. So each is divisible by 2, so that would make a 1/2. So what we have now is the square root of 3 over 2 root 2. Again, we want radicals to be simplified, fraction to be simplified, and no root in the bottom. So we're almost there, except we still have that square root of 2. So anytime you have a radical in the denominator and you can't get rid of it by simplification or by simple simplification, you are going to have to rationalize. So we've got the square root of 3 over 2 root 2. So when I rationalize, I'm creating an equivalent fraction. To create an equivalent fraction, you have to multiply both numerator and denominator by the same thing. So I'm going to multiply them both by some square root. Again, so you want it to be that when you multiply this radicand by this radicand, that you get a perfect square. So what can you multiply 2 by so that this 2 times that number is a perfect square? And the easiest thing would be multiply 2 by itself, right? If you multiply any number by itself, you end up with a perfect square. So what we have now is the square root of 6 over, so we have our coefficient of 2, and the square root of 2 times the square root of 2 is the square root of 4. Okay, we're almost there. That's the purpose of doing this, was to get rid of our roots, and we can because the square root of 4 is 2. So 6 is not divisible by a perfect square. I can't do any simplification there. So what I have is the square root of 6 over 4. Okay, I cannot reduce, right? There are no numbers out front, no coefficients to reduce with that 4. The square root of 6 is a simplified radical, and I've got no roots in the bottom. So all 3 of my conditions are met. So I can stop. Okay? So it's going to take some time and it's going to take some practice. And, you know, lots of routes you can take, lots of steps you can do next. But as long as you just kind of keep going with it, always keeping in mind, I need to have fractions simplified, I need to have radicals simplified, I need to have no roots in the bottom. And you may not take the most efficient route, but as long as you get to the end result, that's all that really matters. Okay? And we'll continue with more rationalizing in the next video.